紹介いただきましてありがとうございます。
Thank you for the introduction and good morning. I'm Yang, CEO of Qunasys. Thank you for joining us early in the morning. So Qunasys, together with QCware, we're very honored to host this event. So I want to thank QCware first, and I want to thank all the sponsors, the many sponsors, and the many participants for making this possible. So you have come early in the morning. I was thinking what I should talk about today, and I think that you're interested in how to commercialize quantum computing. And I think the fact is that we have not made a useful quantum computer yet. So for what kind of application would the quantum computer be useful? That what part I think is important, but I think that's addressed by various other talks and tracks. So I like to talk about the how part, how to create the ecosystem for quantum computing so that people can come into this field and to accelerate the progress of this field. In thinking about that, I'd like to look back in history. I think that may be significant. Classical computers and machine learning. I'd like to learn from those histories and think about what is necessary for quantum computers and going forward. So that's what I'd like to talk about today. So quantum computing. I'd like to talk about the industry of quantum computing. And as you know, quantum computing investment into universities and startups, that has been increasing year after year. It's a little old information, but you see 2016, 17, 18, well, a similar trend continued in 19 and 20. And because of the poor economy, I think it might decline this year. But from around 2016, there was a start of investment into startups. But in terms of number of companies, maybe we have peaked out. And 2017, 18, we saw the peak in the number of companies that were started up. And quantum computers, well, it can be used in this way. So, well, it's not an industry where you can have a specific application. You have to do research with university professors and try to commercialize. So the prominent professors, they could make their own startups, and I think we have seen that course that run its course. Now, let's look at the history of classic computers to think about quantum computers. In 1980s, in the computer industry, we saw the shift from mainframe, or it was started to be used in mainframe, and you had the IBM chip and IBM hardware. So you buy that mainframe computer, and you had the IBM OS, and they had the application on it. So it was a vertically integrated industry. So that's where the classical computer industrial application started. Now, for IBM, for example, if you wanted to use IBM application, you had to buy the IBM OS and hardware, and if there was some trouble, you ask IBM, they would solve it for you. So that's how the industry started. But as you know, if you wanted to use Microsoft Word, you don't have to necessarily buy Microsoft Surface. So it's shifted to horizontal structure that you see on the right. So I think there are benefits to that horizontal integration. So if you make a niche application, it would not be constrained by the hardware. If you make a niche application, it could work on a variety of hardware. So that was the horizontal integration that became prevalent in this industry. And you know, I think you've seen the chaos map of quantum computing. So there's Google, IBM, various other startups making quantum hardware. Then there's the electronics that control that. The companies do that. And then there are companies that make applications. And So quantum computers, I think upfront investment is continuing. And so I thought that we would start from that horizontal structure that you see on the right. But we see a different trend recently. For example, Cambridge Quantum Computing and Honeywell created a Quantinuum JV, Q&Co, a Dutch company, a software startup for quantum that joined with Pascal. And then Supertech, or Cold Quanta, bought Supertech. So in this industry, well, we've seen this kind of interesting news that we're starting to see some vertical integration. And the financial reason is that it's better to raise funds together. And I think the major factor is that hardware and software, by having a strong fusion between the two, you can provide more value to the users. I think this is one big trend we're seeing. So even if it works as software, you may not be able to maximize the performance of the hardware. It's a little difficult to optimize if it's a separate company. So by integrating, you can design the hardware based on the requirement of the software. So that's why we're seeing this kind of integration in the industry. Now, but also there's the horizontal structure, that platform structure that exists, like the IBM and the AWS. So sorry, it's a busy slide. So what they're doing is that the people who develop software, end users, developer like us, they can place their software on this, and hardware and software in a hybrid manner will collaborate. That's the system that's being offered. And so hardware and software are collaborating. This kind of form is also being developed. So this is another trend that we see. So how is the industry going to evolve? It's unclear. I think it's interesting to watch. And I think that the horizontal structure was aimed for, but we're seeing vertical integration. And until there is that quantum superiority, we might have this kind of strong connection. And so if you have various applications, different applications available, then we will see separation of hardware and software. And so quantum computing hardware, I'd like to talk a little bit about that. So in talking about hardware in Japan, we can't not mention this, that the first quantum bit was made in Japan. Dr. Nakamura and Dr. Atsai at NEC created the first superconducting qubits. You see the green and red. It's 0 and 1. And so the current flow, and you're able to create a superposition. And so that's the world's first superconducting qubits. And the performance of qubits has been improving year after year. Looking at the coherence time, how long can you maintain the superposition of 0 and 1? In 1999, it was nanosecond level. But the more recent ones, like IBM device, you see lower right, ABGT1, 300 microseconds. So 10,000 times, 100,000 times coherence time has been achieved with the qubits. So we're seeing innovation here, and we're seeing great performance in these qubits. And I think what's iconic in Japan, the quantum machines actually installed. So in Kawasaki and the University of Tokyo, IBM machines have been installed, and we see an environment where many companies can use it, and students can play around with it. And it's important, significant that this is now available. So when these machines were installed, you had to look back on the history of classical computers, and that's what I did. And so digital computers after the war in Japan, when it was introduced for the first time. Maybe it was a coincidence. I don't know. It was IBM. So digital computer, it was introduced by the metrology agency. So it was this kind of device. So this went into the metrology agency. It was a computer center. And many people came together, and many people did various computation on this digital computer. It was sort of like a hub, computing hub. So I looked up the history of that time, and it's quite interesting. In the past, there was no sophisticated reservation system. So they would write in a notebook, they wanted to do this kind of computation from what time to what time. So if you look at the notebook, you can see what other researchers were doing, what kind of calculations they were making, and then you could imitate that. And so based on that, you could talk to that person and ask for know-how to be transferred. There was no GitHub at that time. That was how knowledge was transferred. So usage know-how was shared in that kind of a consortium, in that kind of a shared machine center. And then members who graduated from that, who went their own ways, they had the technology to use these digital computers and went to other industries. And then they established computer hubs in their industries and disseminated the know-how and technology. And because we had this kind of shared center, the utilization of digital technology flourished in Japan. So, in the early ages of classical computers, sharing of knowledge accelerated industrialization, and in quantum computers, we're seeing interesting devices. And there are some devices that are starting to show quantum supremacy, and use cases may include exploration, and that kind of knowledge will be accumulated and lead to competitiveness. Now, many users are looking for use cases. I think the other important factor is algorithm. So there was that paper about quantum supremacy in Nature. It's the last word there. In 2019, Google demonstrated quantum supremacy. So when you simulate the circuit in a supercomputer, you have the more powerful simulation on the quantum computer. So it's an application that's not useful for industry, but by this development, quantum computer, you can have the superposition of 0 and 1, and you can make possible what was impossible before. And so you're now simulating quantum circuit, so it's useless industry-wise, and in order to reach a usable application, maybe you can map this kind of a problem, and this could be solved by the quantum computer. Then that could lead to industrial applications. So developing creative algorithm is going to be important. So this Google's quantum supremacy, that quantum circuit that can be simulated easily by supercomputers. And so whether or not quantum supremacy was actually achieved is not clear, but clearly there are things that we could not achieve with supercomputers. We're trying to achieving that, or Xanadu or Chinese university device. They're also showing supremacy. Now, looking at the decryption of RSA encryption key, so you have this algorithm for that. 1 billion, 10 billion qubits were necessary, it was said. But with improvement in algorithm, we see you need now 20 million, so there's a 100-fold improvement. And what we're doing at Qunasys, variational quantum calculations, so there's an application to look at the most stable state, and you can calculate the force of the molecule, and you can do simulation. And you can look at the excited state of the molecule, and you can use it for designing of OLEDs, or you can do periodic calculation to design catalysts. So based on an algorithm, it can be applied to various industrial applications. So fundamental improvement of algorithm and applying to industry. Those are areas where there's a lot of research, but as I have been saying, it has not become commercially usable yet. There's a lot more work to be done. So what is necessary for research going forward? That's what I'd like to talk about a bit. So very quantum eigensolver, I use that example. VQE, what does it do? So you create a certain molecule status, and you tune the parameter of the circuit, and you have to measure with quantum computers, and then you have to update the parameter many times. And what's more problematic is that more qubits you have, the parameter tuning becomes even more difficult. And so quantum computer, people say you can't use it because there's no noise. Even if you have a device with very low noise, because of this problem, it will not be easy to use this conveniently for industrial applications. And so algorithm research, how should we promote it? I would like to give you my personal view. And what I think is quite important is to develop index or indicator. So benchmarking was discussed yesterday. So at the time of Industrial Revolution, the steam engine was created, and that was improved at a very fast rate, and that led to locomotives, and that supported industrial revolutions in many ways. What was important was measurement tools. So steam engines, what would be the horsepower to measure that accurately? So with this technology, you will improve horsepower by 10%. Then people will adopt that and improve that further. So to have that kind of benchmarking is important, and you can, based on that, you can have an idea and feedback and further improvement by engineers. And I think that supported the Industrial Revolution. Now, more closer example to quantum computing, I think machine learning would be that example. In 2010, ImageNet was established for image recognition. That's where the boom for machine learning started. So 2010, ImageNet competition was conducted, and many large data set was prepared, and you would categorize the images by the machines, and you look at the accuracy. When it started, it was about 28% error rate. Next year, it went down to 26%, 2% improvement. But then the year later, it was a 50% improvement. The reason is, as you know, deep neural network at this time was used. So suddenly, the accuracy improved by twofold. So when you define the indicator, and if the researchers can work based on that indicator, then that leads to great improvement in the methodology. So I think this gives us many important lessons. So for quantum computers, there are already competitions, but it's a one-off thing. Or if you do it just once or twice, you just get a minor improvement, 28 to 26. So how to continue that kind of contest, I think, is going to be important. You have to define that indicator, and you have to measure together. So if it was not defined, the neural network may not be used, and Jeffrey Hinton's paper may not have been appreciated. So to have this kind of benchmark and have that accurate evaluation is necessary. So what we think, what we feel as Qunasys in quantum computer, like improvement in VQE, when you actually implement it, it's the results are different from what was thought. And so how to define that indicator is, I think, quite important. So based on this machine learning and image recognition, I think it's important that we have a benchmark to evaluate the performance. so that the researchers can compete with each other in improving the technology. Lastly, several years ago at Q2B, this was quite interesting, so I want to share it with you. So in electromagnetism, well, that was a study that developed to light up the night. But as you know, humankind, by controlling light, they made motors and semiconductors, and that led to mobility, automation, communication, so expanded to various fields that really updated humankind. So what we're aiming for is to control quantum mechanics. That is the challenge we're working on. And so in this conference, we're focused on computing. So computer where you control quantum mechanics. So sensors, communications where you use quantum mechanics. And I think this industry is going to expand. By controlling quantum mechanics, you can create many new things. That's quite possible. So quantum computer, people talk about simulating materials, but by controlling quantum mechanics, new science will be born. Based on that, new technology can be developed and spread. So if you aren't already in the industry, I hope that you will join us. So Q2B 22 Tokyo, thank you for coming to this show. There are many interesting talks lined up for today, so please look forward to it and please enjoy them. Thank you very much.